All right, welcome to NOAA Live. My name is Grace Simpkins, and I'm going to be moderating today's webinar. This series is sponsored by NOAA's Regional Collaboration Network, which is spread across the country and helps connect people to all that NOAA does. It's also sponsored by Woods Hole Sea Grant, where I work, which is located at the Woods Hole Oceanographic Institution here on Cape Cod, Massachusetts. NOAA Live webinars will be offered most Wednesdays at 4 p.m. Eastern Time, and you can follow us on Facebook or you can check out our website to see what's coming up. Now, this series is designed to help you get to know NOAA and some of our incredible experts. And as you may remember, NOAA stands for the National Oceanic and Atmospheric Administration. Now today, it's my pleasure to be introducing you to Meg Chadsey with NOAA's Washington Sea Grant and the Pacific Marine Environmental Lab in Seattle, Washington. And while we'll be speaking about NOAA's role in studying ocean acidification, we want to recognize that we are all coming to you from the traditional lands of Native communities who have substantial traditional and local knowledge and much to share with us. We acknowledge that Meg is coming to us from the land of the Coast Salish people, including the Duwamish people past and present. Meg's work touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We are hosting this webinar from the ancestral lands of the Mashpee Wampanoag tribe and the Wampanoag tribe of Gayhedaquina. Now, a few guidelines before I hand it over to Meg. Just as a reminder, you are all muted because we have a lot of people on the line and we want to make sure we can hear Meg. However, don't forget to write your questions in the box. I'll be keeping track of the questions, and every now and then Meg will stop and answer a few. So we may not get to all of your questions. We'll try to answer as many as we can. And for Mrs. High Race class, please tell us who's asking the question so we can call out the student that gave us that question. Now I know that you are very eager to see what Meg has to tell you. So I'm going to turn it over to you, Meg.
All right. Thank you for inviting me to be part of this show. I'm very excited to be speaking with all of you. You are probably looking at a picture of me. I probably be about 2 years old and on a beach. And like many people who work at NOAA, and probably many of you as well, I wanted to be a marine biologist since the very beginning. And I was lucky enough to grow up in Washington State in the Pacific Northwest. This is Washington, they're up in the corner. And with plenty of beaches to explore. You can see that the western half of our state has touches the ocean in many places. And my family I grew up on this island, Vashon Island here in the middle of this inland body of water that we call Puget Sound. Sometimes we also call it the Salish Sea. And we also took vacations on the outer rocky coast of Washington State. That's probably my favorite place because the tide pools there are just amazing. And that's where that picture was taken, by the way. And now I live and work in Seattle, again, along the shores of Puget Sound at Washington Sea Grant and for the NOAA Pacific Marine Environmental Lab. Now, the Pacific Northwest, Puget Sound, and Washington's outer coast are famous for their marine life. They're iconic. And salmon, of course, are something that we're known for. And we also are well known for our resident orca whale population. Here you can see orca whales leaping out of the water right in front of downtown Seattle. Here's our famous Space Needle. All the tall buildings are off to the right, but that is right downtown Seattle. Sometimes I'm lucky enough to see these wild orca whales. So less photogenic, but really no less beloved or important to the people of Washington State are our oyster beds. Now, the Pacific Northwest is a terrific place to be an oyster. From the bays of our outer coast to the river-fed waters of Puget Sound, our tide flats are home to many wild and cultivated or farmed shellfish species. And I don't know for sure, but I think the person in this photo is a shellfish farmer. He's got the shellfish farmer boots on. So that's what a shellfish farm can sometimes look like. Now, farming oysters in Washington State is a big business, and most farmed oysters begin their lives in shore-based hatcheries in tanks, where they're spawned and then raised. These are spawning adult oysters, and then the babies are raised until they reach this stage. It's called seed stage because they're about the size of a seed. They look like an oyster at this point of their lives, and they'll just continue to grow bigger and bigger. And oysters are usually, they leave the hatcheries at the seed stage, and then they're planted out in the open water on those tide flats to grow to market size. So here is a microscopic image of a baby oyster when it's probably only a few days old, right after it has formed its first shell. You can see it looks a little bit like a tiny clam, and it has transformed from a ball of goo, which is what it was the day it was created, into something that is recognizably a shellfish. And just like human babies, baby oysters are most vulnerable during this very early life stage, during the first few days of their lives. And the people who run the shellfish hatcheries, the hatchery managers, they take great care to make sure that the water coming into their hatcheries is clean and that these baby oysters have lots of microalgae to eat. Now, you've tuned in today to learn about ocean acidification, and you're probably wondering, what do oysters have to do with ocean acidification? Well, we wouldn't know as much about ocean acidification or its effects on shellfish today and other marine species, actually, if it weren't for those vulnerable baby oysters and the hatchery managers. Because although ocean acidification is a global problem that's kind of been sneaking up on us for decades, it didn't really get much attention until about 15 years ago here in the Pacific Northwest, when the baby oysters in our hatcheries started mysteriously dying. And when managers and scientists finally figured out what the problem was, and it was that ocean acidification had caused the seawater to become so corrosive that the baby oysters couldn't form that first shell and they couldn't get past that life stage, those people sounded the alarm and the whole world started paying attention at that point. So I'm going to pause right here and take some questions.
Thank you, Meg. Yeah, so we had a question come in from Marilee, and Marilee is wondering, what is acidification when you use that big long word?
Marilee, I'm glad you asked that, because scientists are very picky about the words they use to describe things. They want to be absolutely accurate. And acidification means getting more acidic than you started out. So it doesn't matter if you are acidic already. If you become more acidic because of something happening to you, you are acidifying. That's acidification. Or you can be not acidic at all and get a little more acidic, and that is also called acidification. It's kind of like warming. You can be cold and get warmer, that's called warming. It can be a hot day and you can get even hotter, that's also called warming.
And Meg, would it be fair to say that something that's acidic means that it's corrosive, or like for those maybe that aren't familiar with the acidic part of it?
Yeah, it is fair. The question is corrosive to whom? And we're going to talk about this a little bit. Seawater is corrosive to some marine species. I mean, acidified seawater is corrosive to some marine species because they have shells and hard parts made of calcium carbonate. But it's not corrosive to our skin. Our skin doesn't react with acid in the same way. And the acid is not really a very strong acid, so we wouldn't feel it, but it does matter to things with shells. It is corrosive to them.
Okay, I'm going to share two questions with you that I know you're going to cover, so I don't want you to answer them yet, but I wanted to call out these folks. So Texas asks, what causes ocean acidification? And Meg is going to tell us, so that's a little preview. And Stephen asks, what is the average normal pH of seawater versus the pH that doesn't allow shells to be formed? So I think you're also going to touch on that. So I just wanted to give you those as a lead-in. But Cora asks, how long does it take for a baby oyster to get to be full grown?
Again, scientists always answer questions with "it depends," and that's true here too. It depends on the species, and it depends on what you mean by full grown. A farmer wants to raise an oyster to about this big. This is the size of oyster that people like to eat. They don't like to eat big, chewy oysters. So they try to raise them to about this size. And the species that we raise here most in the Pacific Northwest, the Pacific oyster, takes about 2 to 3 years to get to that size. There was another part to that question, but I don't quite remember. So
She just asked how long it takes for a baby oyster to be full grown. So I think you got that. And I'm going to hold on. Like I said, Texas and Stephen are asking about things that you're going to get to. So I think what I'm going to do is let you go on because I think some of the questions will be answered. And if you have any questions that do come up while Meg is telling us more, share those and I'll ask those at her next pause.
Okay. So yes, I am going to tell you what ocean acidification is. We're going to talk about that together. So ocean acidification is sometimes called global warming's evil twin. And that's because they're both caused by the same thing. They are caused by excess carbon dioxide that humans are putting into the atmosphere and the oceans because we burn things like fossil fuels and we are clearing forests. And we're putting, as we burn those things, the waste product is carbon dioxide. And it's going into the atmosphere. And here is a picture of that. So I have this generic factory cartoon, and there's a cloud of something coming out, and the little CO2 molecules, that's our shorthand for carbon dioxide. So it's entering the atmosphere. And we all know, I think, what this excess carbon dioxide that we're putting in the atmosphere does up there. And behind me, I think you can see me, I use a down jacket analogy to talk about this. So my down jacket, which I need in the Pacific Northwest in the wintertime, all the time, is very lightweight. There's, not much to it, but when I put it on, it traps a lot of heat and I can feel very warm with just a few ounces of jacket around me. So carbon dioxide in the atmosphere acts a lot like a down jacket and it traps heat on our planet. And that is why we continue to set heat records year after year as our planet gets warmer. Now, not all the carbon dioxide stays in the atmosphere. About a quarter of it is absorbed by the oceans, and there it reacts with seawater in a chemical reaction, not a physical effect. It reacts chemically with seawater to form an acid, and that is why we call it acidification. Sometimes I think my job is so easy to explain. It's not a very complicated process. But I want to, before I move on to the next slide, I just want to point out that I borrowed these two images from my friend who has a wonderful video about ocean acidification that you can find on the NOAA live page, and it's called Nemo on Acid. And I just hope you find time to watch that. Okay, here is that reaction that we were just talking about. Another friend of mine, Zoe, painted this for me, and she represented carbon dioxide as these little red bubbles, and they're up in the atmosphere because they've come out of our smokestacks, and now they are dissolving into the seawater. And so those molecules of carbon dioxide meet a molecule of water, and they form a new molecule called carbonic acid. And that, again, is why we call this acidification. So it may not have taken very long, but I want to pause again for questions because sometimes people really want to ask about the chemistry. So I'll stop here for a sec.
Okay, this is Grace from the chat box. So if you have any questions about the chemistry, please let us know if that didn't make sense. And I will share, because you started talking about oysters, Meg, and there's a lot of interest in oysters. We did have a question come in from Mrs. Hiray's class. How many types of oysters are there in the world? Do you know? I
don't know. No one has ever, good job. No one's ever asked me that question in 10 years. We have several species of oysters that are raised, that are farmed for eating here in Puget Sound. And the one that we grow the most of, the Pacific oyster, actually isn't from here. We brought it to the Northwest from Japan, where it is native. We also have a native species of oyster called the Olympia oyster, and it's a slow-growing oyster. It takes much longer to reach a big size, but we're trying to bring that species back. And I think there are a few other types of Japanese oysters, and also the Atlantic oyster we are able to grow here in Washington. But as far as the whole world, I bet just a lot more than I just listed, but I don't know.
Yeah, so we have a few more questions on oysters. Are there male and female oysters? Bodie asks.
Yes, And I have just been learning about this myself. It's hard for us to tell from the outside if an oyster is a male or a female, and I just learned that some oysters start as one sex and then they change to a different sex in about a year, for reasons that are probably known for sure only to them, but it may have to do with recruiting mates. So probably the answer is both.
That's one of the fun facts I always share about oysters when I'm talking to folks. Now, just to get at the chemistry, because we've so I know there were oyster questions, but now we're going to move on to the chemistry. Scarlett asks, what is carbon dioxide? So maybe you could just remind Scarlett that it's a clear gas, you know, where it came from.
Yeah, I just went back a little bit on my slide. So as I said, we use the shorthand to represent carbon dioxide, but it does tell you a little bit about what it is. So the C stands for one molecule of carbon, and the O stands for oxygen, but this little number 2 here means there are two molecules of oxygen attached to one molecule of carbon. It's sort of like a little triangle shape, and that altogether is a molecule of carbon dioxide. Great question.
And if you could just go back one more slide, Meg, I think just to remind Scarlett that when you talk about carbon dioxide, it's a gas that's that's all around us right now. You can't see it, but it's something that's produced when you burn things like oil and coal and gas. So that's Meg's image right there where the carbon dioxide is coming out of that factory.
Yeah, no, Scarlett, you've set me up for the next slide really well. If we're done asking questions,
I'm going to let you move on, Meg. Yep.
Okay. There we go. Whoops, nope, not that slide yet. Because it is hard to talk about carbon dioxide and what it does because it's invisible. So we can sometimes only see the effects of having too much of it, but it's hard to visualize it. So what we're going to do now, some activities together to help us understand what acidification really means. We're going to make the invisible visible, sort of. We're going to use colors, changing colors, to see what effect carbon dioxide has on things. And so this first activity that we're doing is called Red Cabbage Ocean Acidification in a Cup activity on the NOAA Live page. And you can go there and do this yourself at home. Everything is easy to make, easy to find, and cheap and non-toxic. So I hope you will practice this at home and amaze your friends. So before we start the demonstration, I just want to show one slide so I can explain what's going to happen a little bit. This beautiful rainbow of vials with liquid in them. Each of those vials contains a tea that's made by boiling red cabbage leaves in water and just letting them sit for 10 minutes. I call it red cabbage juice. And the remarkable thing about red cabbage juice is that it contains a pigment from the cabbage that changes color depending on the acidity of the solution that it's in. So things with a very high level of acidity on this side where it says strong acid, on the left, the pigment will turn kind of orange or bright pink. And solutions with a very low level of acidity on the other side, over here, you have that kind of teal to greeny yellow. And when the experiment that we're doing today, and I'm going to hold this up, I can't see you, but I think you can see me. So I hope that you can see this glass I'm holding up in front of my face. We're starting with some tap water that has cabbage juice in it. And tap water is neutral. It's neither acidic or basic. And so it's right here in the middle. And the middle color is this kind of purpley blue. All right, so just a second. I'm going to stop sharing my screen. And perfect. Great. Okay, so now we're going to do the demonstration together. The first thing we're going to talk about is acid. All right, what is this, folks? We know what this is. Michael is guessing. He's probably signing that this is a lemon. We recognize it, and we know lemons. We know what it feels like to get lemon juice in a cut. You might have gotten lemon juice in your eye sometime, and it stings and it burns. That's the acid, folks. There's a lot of citric acid in lemon juice, and it's quite a strong acid. All right, so we are going to put a little bit of lemon juice into the cabbage juice and see what color it happens. Now, based on that slide I just showed you, you probably have some predictions, but let's see what happens in real life, because sometimes things never go as planned. So I'm going to squeeze the lemon juice in, and I'm going to hold it really close. The light's not so good. And I'm going to swirl it around with my finger. Okay.
Oh, we can
All
see
right,
that.
you can
Don't you
see
worry.
it.
We can, everybody, write in the chat box if you can see it.
All right, so compare the colors. If you were in the room with me, I think it would be brighter, but you can see that we went towards that acidic side of that rainbow scale. We're down there where things are pink, and it's a big change. So very acidic, big color change. Now, someone, I think it was Scarlett, asked earlier, it was a good question. It's about where does carbon dioxide come from? And you answered that it comes from burning fossil fuels, and I said that too. But there's another place carbon dioxide comes from, and that's us. Because you can kind of think of us as cars, except we don't use gasoline, we use pancakes or spaghetti or whatever you had for breakfast. And we burn that fuel with oxygen inside of our bodies, inside our cells, just like a car burns fuel with oxygen in its engine. And our waste product, just like a car, unless you have an electric car, is carbon dioxide too. So I always have carbon dioxide with me to do this demonstration, and I'm going to do it right now. I'm going to blow in here, and you can guess, sort of, I'll hold up the paper. I want you to think about what color you think it's going to change while I blow.
Okay, so while Meg is blowing, just as a reminder, she is blowing out carbon dioxide because that's part of what humans do, right? We take in oxygen. So watch the water as she introduces carbon dioxide. You want to guess, do you think that that's going to make the color change go in the same direction as that lemon, or do you think the opposite direction? Oh, Meg ran out of blowing power.
I ran out of breath, and so I'm just going to hold up. You're probably thinking this experiment didn't work because you didn't see much of a change, but there was a change. Oh my gosh, yeah, okay. It's subtle.
We can see it. Yep, a very slight change.
See that this one is a little lighter color. All right, so if we went back to that rainbow slide, you would see that it's a little bit closer to the acidic side of the scale. It did change, but it changed a little bit. All right, and that is actually exactly what I want you to see, because I don't want any of you to be afraid to go to the beach and swim because you think that seawater is going to be so acidic that it will sting and burn you. That's not what's happening. This brings us back to that what is corrosive mean question. This small change in seawater acidity we can't detect it, but some marine species, it does make them uncomfortable. It becomes more corrosive to their shells, which are made of calcium carbonate. So before we move on to the next, well, this is the next demonstration, we can all experience what a small change in acidity feels like ourselves in our own bodies. And to do that, we're going to hold our breath together while I count to 10. So are you ready? And let your breath out after 10. We'll just do it, okay? You too, Michael. Ready? Okay, so I bet that a lot of you started to feel like, oh, it would be nice to take a breath right now. No one's passing out, I hope. But that discomfort that you feel when you're not breathing, when you're holding your breath, and that need to breathe, that's your brain setting off an alarm. Your brain really wants that oxygen. We know we need oxygen to live. And so your brain, when you're not breathing in and getting oxygen, starts to send off these signals that says, please take a breath. But the interesting thing about this is that your brain can't measure how much oxygen is in your body. It can only measure how much carbon dioxide is in your body. And it does that by measuring the acidity level in your own blood. So when you hold your breath, you're not bringing oxygen in, but you're also not pushing your waste CO2 out. And so it is building up in your blood the same way it is building up in seawater. And that same reaction with water happens so you're making little carbonic acid molecules in your body. Don't worry, it's not enough to hurt you, but it's enough to make your blood just a tiny bit more acidic, and your body can notice that. So we can feel small changes, and so can marine organisms. All right, I'm gonna pause here for questions before we go on to the last demonstration.
Okay, Meg, so we had a question come in. Katja is wondering, does temperature have an effect, or does temperature matter?
Temperature matters a lot. Yes, and it's kind of a complex, this is where things get complex. But you know that the planet overall is warming and the oceans are absorbing some of that heat, so oceans are also getting warmer, and that does affect kind of the balance of chemistry in the ocean, so that it can affect the rate and the level of acidification. So maybe not the way you'd think. Colder oceans tend to hold more carbon dioxide and be more acidified than warmer oceans.
And Juana's wondering, when you study ocean acidification, do you get to go out and like in the field much, or is most of it in the lab?
So I am no longer doing any lab science myself at all. I have, for me, the perfect job. I get to let everybody else put in those long hours and do sometimes repetitive experiments and figure things out. And then they tell me, or I talk to them about it, and then I get to tell you. So it's like the best of both worlds. I sometimes do get to go out with the scientists, and field days are some of the best. So that's a cool question.
Excellent. And Raina wonders, how many species are hurt by carbon dioxide? And if that's something we're going to get to, then you can hold on to that, or if you want to field that question.
I'll give you a short answer. I know that in Puget Sound, where I live, there's a group of marine species called calcifiers. These are all the species that have shells or exoskeletons or external hard parts made of calcium carbonate, and at some point in their lives. And that's about 30% of all the marine species in Puget Sound. So about a third are directly vulnerable to the effects of acidification, which is the next demo that we're going to do. But then later on, we're going to find out how even more species can be affected by acidification. That's a perfect question for what we're doing next.
Can I ask you one more question before you move on?
Yep.
So Aiden asks, can the acidity level increase affect the intake of oxygen by fish? So if you see ocean acidification, does it impact how much oxygen the fish can take in?
Oh, you guys are getting right into the tricky questions. So yes and no. We know that acidification happens because more and more carbon dioxide is entering seawater. And that extra carbon dioxide kind of crowds out the oxygen that some fish and some species like squids tends to be the creatures that are like the racehorses that can go really fast, that have really high metabolisms. As the CO2 builds up in the ocean, it makes it harder for them to get all the oxygen that they need. So some species that don't have shells, like tuna fish, may be directly affected by carbon dioxide, not necessarily the acidification effect of it, but the carbon dioxide itself. That's a really great question.
Great. I'm going to hold on to the rest, and I'm going to let you move on.
Okay. So the last thing we're going to do, I always return to this activity after a hold a breath question for exactly the reason that just happened, because while some species do have that like breathing issue with ocean acidification, that's not nearly as common as the effect of acidification on animals that have shells. So this is an oyster shell, a Pacific oyster, market size, and it's made of calcium carbonate. So I have a cup here. It looks like water, but it's not. I'm cheating. This is white vinegar. So like lemon juice, it's pretty high in acid. And so I'm using vinegar instead of water with carbon dioxide in it because vinegar just speeds up the reaction that I want to show you. If I put this shell in water with carbon dioxide in it and we all waited for about a week here on GoTo, you would see something, but now you're going to see it right away. So I'm holding this up above my keyboard, and I bet you can all see really well the bubbles that are coming off that shell.
We can see it. It looks, we can see them rising, so you've got it in just the right place, Meg.
Great, this worked better than yesterday. So those bubbles are evidence that the acid in the vinegar is attacking that calcium carbonate shell and actually dissolving it. And that's That's a pretty good proxy for what acidification is doing to shelled organisms. It's more complicated, of course, but things that are made of calcium carbonate tend to dissolve or want to stay in solution rather than being hard, solid substances as the water becomes more corrosive because of acidification. So let me see, okay, now I'm going to switch back to slides. We've done the last demo, so give me just a second here.
So while you're doing that, I'll just tell the folks at home that in addition to doing the experiment that Meg did with the cabbage juice, if you have shells at home, like a clam or an oyster shell, you can do what Meg did with vinegar, because vinegar is something you might have in your cabinet. So that's another experiment that's very easy for you to do at home. And Meg, we don't see your slides yet.
Yep, no, I'm about to share them.
Okay.
Do you see them now? Is that good?
Yes, perfect. I see a very cute pteropod.
That is a pteropod. Now, I bet some of you know what pteropods are, but for those who haven't heard of these just adorable little tiny marine snails, I'm going to tell you a little bit about them. So right up here, as the sign says, this is a pteropod, and they're a type of marine snail that swims through the water column instead of crawling along on the surface of things. And like oysters, they have calcium carbonate shells. And you can see from the picture that they're very smooth and very thin. They're transparent. By the way, this is a tiny, tiny creature. The one in this picture here, this species is about the size of a head of a pin. And the biggest pteropods that have shells, I think, are smaller than your pinky fingernail. They're small creatures. But you can see that this shell is thin and transparent and very smooth. And in this microscope picture of just an empty pteropod cell, you can really see how beautiful and delicate it is. Now, I am going to start a movie, I hope, that shows you how these pteropods swim. And if this doesn't work, I've got to back up. Yay! It works. Okay, so as I said, pteropods are plankton. They swim in the water, and the way they do this is their foot that most snails use for crawling along has split into two wings, and you can actually, in the next movie, you can, whoops, next movie. Let's try it again. There you go. In this movie, you can really see how it flaps those wings. And if you haven't loved pteropods before, I hope you do now. I love them the most because they remind me of golden snitches. And so I wanted to say that pteropods are in the Pacific Northwest, but they could be the international poster child of ocean acidification because they are in all the oceans of the world. Here, I'll just hit play again, I think. Oops, nope. Anyway, they're in all the oceans of the world, and that's good because they're very tasty and very nutritious, and so many animals in all parts of the world depend on these for food. So they have a nickname that I don't really like called potato chips of the sea. I would rather that they were called the power bars of the sea because they are nutritious and they're so important to the diet of many species like salmon, like birds, and even huge baleen whales will feed on these. So next slide. Pteropods, unfortunately, are experiencing the effects of ocean acidification right now. And the waters along the Pacific West Coast are more corrosive because of acidification than they used to be to creatures like pteropods that have delicate calcium carbonate shells. And if this image and also this image were painted from electron microscope pictures, so they were real live models of a healthy pteropod and a pteropod that was collected from corrosive waters off Washington's coast. And in this case, you can see that the shell is pitted and being dissolved a little bit. And so what we don't know yet is how that harms the animal itself. It looks bad. We're guessing it might not be good for them, but the experiments to understand how this will affect the population are still being done. Okay, here are a few other species from the Pacific Northwest that are also vulnerable to acidification in the same way. Their shells, it's hard to build and maintain their calcium carbonate shells when seawater becomes more corrosive. So up here we have a normal snail. This is called an olive shell snail, and they live nowhere else besides on our outer coast. And they're very important to the macaw tribe. who use their shells for their jewelry and regalia and for ceremony. This is a sea urchin, and sea urchins can be found in many oceans of the world, and their spines are made of calcium carbonate. This is a clam, kind of like an oyster. Same sorts of things are happening to clams. And then recently, more recently, scientists have discovered that even some crab species, Dungeness crab here, are vulnerable to acidification in their early life stages when they also are plankton, and their shells at that point have more calcium carbonate in them. As adults, the shells are made of chitin, which is more resistant to acidification. All right, so it's not only creatures with shells that are affected. The marine food web is so tightly linked, and we talked about how everybody eats pteropods, that you can imagine that even if you are a fish that's not affected directly by acidification, if the things you like to eat start to decline, you might also. And then salmon are the favorite food of our resident orca whale population. So acidification can even ripple out to the dominant marine mammals in the ocean, even though they don't have shells. So I'm going to pause for questions again here. And some of you, you might be thinking about what other marine species are vulnerable to acidification, and I'd love to hear about what you think.
Okay, this is Grace from the chat box. We have a couple of different questions. Allison Paul asked, in the oyster demo that you did, all the bubbles that were coming off of the shell, what gas was that?
Oh man, I was kind of hoping you wouldn't ask that. That's carbon dioxide. And this is, that is not what you would expect, would you? Because carbon dioxide in seawater is what makes seawater more acidified, and then it's that carbonic acid that it turns into that actually would be attacking the components of shells. So it doesn't make sense that carbon dioxide is what comes off when you hit a shell with really strong acid, but that's what I've been told, and I couldn't explain it to you in the amount of time that we have now. So you'll just have to believe me, and I encourage you to go online. I think you'll find good answers to that question online.
I like to give our viewers assignments, so that's a good assignment to give them to look up and research themselves. And Marilee made the comments, I just wanted to share this, that yesterday's NOAA Live, the Alaska one, was on zooplankton, and they talked about pteropods. So if you want to learn more about pteropods, you can watch yesterday's webinar. And Marilee also asked if you could do that experiment on coral. And I said that coral is another good one to do that experiment on. Now, I don't know if you know the answer to this, and if you don't, I encourage you to tell them to look it up. But do you know why, Bodhi asks, they're called pteropods?
Oh, finally, a question I absolutely can answer, and it's a good answer too. So if you remember the flying dinosaurs that were called pterodactyls, that might give you a clue. This root word, the science word, I think it's Latin, ptera means wing. And in the case of those flying dinosaurs, their name pterodactyl translates to winged thumb or finger. And that's because if you look at them closely, they've got finger bones that are webbed and they're flying with those. Pteropod means winged foot. So as I told you, most snails have that foot and they crawl along a surface. But in the pteropod case, that foot has split into two and it flaps like wings. So pteropod is the perfect name for them.
Excellent. I knew you'd know the answer to that one. So let's see. Karen asks, and I think you answered this, but just to say it again. So adult crabs are not affected by carbon dioxide. Is it just developing crabs?
They're not affected, and this is what I know. So if there's better evidence out there right now, I encourage you to go find it. But they are not, their shells are not vulnerable to that corrosive aspect of ocean acidification when they're adults, because their shells are made mostly of chitin, which is what your fingernails are made of. And chitin is not dissolved by carbonic acid or acid in the ocean. But carbon dioxide, remember someone asked about warming and sort of the compounding effects. Carbon dioxide is warming our oceans as well as the atmosphere and the land. And it is also causing levels of oxygen indirectly to decline in the ocean. So you could say that hypoxia, or low oxygen levels in seawater, are the other evil twin of global warming, because carbon dioxide is also behind that. And Dungeness crab, as adults, right now, right this season, are suffering on our coast, on the west coast of the US, because of low oxygen levels. So it is all kind of connected. And poor Dungeness crab, I mean, some animals get it from all these different directions, you know, heat, low oxygen, and increased acidity, and it's all caused by carbon dioxide.
Now, the next question comes from Nikki, and I just want to encourage you, Meg encouraged you, if you can think of an animal that is impacted by ocean acidification, you can share that. So Nikki asked the question, does OA affect sea stars?
I don't think that any lab experiments have been done or field observations have been made that show that acidification is directly harming sea stars. For them, it's more like the Dungeness crab. The changes caused by climate change are making life harder for sea stars, and you may have heard about a massive die-off several years ago on the west coast of the US of many species of sea stars, but most especially our beautiful sun stars. And literally the jury is still out. In fact, they're debating quite hotly what caused that die-off. And I know that acidification and carbon dioxide are not directly implicated in that problem.
Excellent. And before I let you move on, I always like to point out to our viewers that if a situation like that where Meg says they're still trying to figure it out, if that's something that interests you, to me, that shows an area where it might be fun to do some research, right? It's an area where there's a chance for you to ask some questions and maybe get some answers in your career if you're thinking about a career in marine science. So I'm going to pass it back. I'm going to hold on to the rest of the questions and pass it back to you, Meg.
Okay, so for this last segment of our talk together, I want to talk about what we can do about OA, because we care about the oceans. We don't like to see these things happening to the marine species and the environment that we love, and so we want to take action. So I'm going to return for just a minute. I like this graphic example of how ocean acidification makes life difficult for things that need to build shells. So this image of a let's call it an oyster shell, but it's really red and white Legos. But here is a shell that a baby oyster is trying to build for the first time. And it needs the white Legos and the red Legos to build this shell. And in a normal ocean, it has those things both in abundance. In the seawater, it has all the components that it needs to put together. But ocean acidification and the decrease in pH or the decrease in acidity kind of makes those white Legos harder and harder to find. And so a baby oyster will have a difficult time forming its shell because it can't find the pieces that it needs. So here's a picture of the oyster life cycle. And I told you that the picture I showed you in the beginning of oysters that had just formed their first shells, and they were a couple days old. In between the egg getting fertilized, which is day 0 of an oyster's life, and about day 2, where it forms its first shell, this amazing creature undergoes this immense metamorphosis, this transformation. It changes 80% of its whole body weight into hard shell, and that's a lot of work. Now, it gets energy to do this work from a yolk sac that its loving mother oyster packed for it when she first released the egg into the water to be fertilized. And I'm sure, like your mothers or fathers or guardians, the mom oyster would give the baby everything it could to have a good life. But it has millions of babies, so it can only give everybody a little bit of yolk. And it's just enough food. It's like a sack lunch. It's just enough food to feed the oyster until it gets to this stage with its shell, which is when an oyster can begin to feed itself. So if you're think back to that Lego game and you're a baby oyster and you're not finding the pieces you need to build your shell, and this stage takes longer than it should, you might just plain run out of food and die before reaching this stage. And that is actually what happened in those hatcheries. And the hatchery managers were able to fix this by just adding antacid basically to the water in the tanks and bringing lowering those levels of acidity so that this process here became as easy as it always was for an oysters. And that fixed the problem. And it can continue to fix the problem in the hatcheries. But what do we do when those seed oysters are big enough to get planted out into open water where the water can be corrosive? How can we protect these earlier life stages? And I said that I would talk just a tiny bit about kelp in my talk. Kelp is being explored right now as a way to kind of shelter vulnerable organisms with shells like oysters, like mussels, from the effects of acidification. And the idea is that kelp, just like plants on land, they photosynthesize and they pull carbon dioxide out of the air if you're on land, but the water if you're a piece of kelp, and they use it to form their own bodies. So if you have kelp in the water, it's going to be drawing the carbon dioxide levels down. And the idea is that will also draw the level of acidity down. So maybe growing oysters and mussels and other shellfish in very close proximity to kelp can actually create a little halo of less corrosive water that will allow them to grow up and be protected even outside the hatchery. So people are experimenting with kelp, and I think in a little while you're going to hear a NOAA Live talk about kelp farming. So I won't say any more about that. But here's the idea that kelp may be able to kind of return the seawater to one that allows the baby oysters to find all the building blocks they need. Okay, well, that was backwards. All right, so I'm going to end because we're not all kelp farmers and we're not all shellfish hatchery managers. So what can we and what can you do about acidification? Now, normally I will talk through this slide and tell you what I think is going on in these pictures because these are all examples of solutions or things we can do to help. But I want to invite you all to either tell me what you think is going on or tell me your own solutions for acidification in the chat box, and then Grace will read those.
Okay, so this is Grace from the chat box. So Meg's question is, do you see some solutions, things that you can do to prevent ocean acidification in those pictures? Or can you think of any ideas that maybe aren't pictured, but you think might be something that you could do to impact this problem? So Eve says alternative energy. Mrs. Hyre is saying solar, I think in that top left picture. The class is saying that there are solar panels on the roof. And James is saying solar panels. Let's see. Mrs. Hyre's class is also saying you can bike to work or to school instead of driving. I think that person has bicycle, and I think they're next to public transportation as well, aren't they?
Yep, I do that sometimes. I do the train bike thing and it works great.
And let's see, Eve says you can do beach and other cleanups. So looks like in that lower right-hand corner, there's some cleanup going on. Bodie suggests saving energy. So I'm guessing that means trying to use less energy in your house. So turning off lights, turning the heat down if you don't need it up. Marilee suggests wind turbines, and Bodie said yes. I was right. That was what Bodie was trying to say. Thank you.
Okay.
Iden asks, is it useful to throw seaweed back into the sea? Because you talked about the impacts of seaweed. Would it be useful to?
Yeah, so I don't think throwing, like if you're talking about finding a pile of seaweed that's washed up on the beach and throwing it back in, for reasons that are, as usual, complex, and I don't have time to explain, that would also make ocean acidification a tiny bit worse, throwing decaying seaweed back in. But growing more seaweed or kelp, or more importantly, and that's what this picture stands for, is preserving the native wild kelp beds that we have and protecting them from harm. That can very locally probably mitigate or counteract acidification. So yes, more kelps and seaweeds, probably good. The big question is, can we grow enough of it to really make a dent in the total ocean acidity levels overall? And that's probably not possible.
And I just want to ask before you talk about it, does anyone have any idea why that middle everybody poops sign is there? Anyone have any idea why Meg may have put that up there? I'm going to give you about 10 seconds to weigh in with why you think it's there, and let her explain. Bodie says, nope, don't know. Scarlett thinks maybe it means that you should clean up. So we'll see. You have 5 more
Yeah.
seconds.
Okay, so poop, and I can't believe that you didn't all just latch right onto that. Again, indirectly, poop can make acidification worse. And I don't want to go into the reasons why, but anything we can do to keep poop out of our marine waters is going to help. And I'm talking about animal waste, of course. So pick up after your pets when you take them on walks. Never let that poop run into the water. Farms, like with a lot of cows or pigs or something, keep those animals back away from the waterways so their poop doesn't get into it. And then people, we're responsible for the most poop on the planet, pretty much. There's more of us than just about anything. So we need to take really good care of our waste stream and have really state-of-the-art sewage treatment plants that take the nutrients that are causing harm out of the poop before it gets released into the water. So my last slide is just to remind you all that you are extremely powerful advocates for addressing ocean acidification. It says knowledge is power up here. You now have some knowledge about acidification, and I promise you, if you care and you share this knowledge with adults and you tell them how important it is to you to do things we know how to do to address ocean acidification, they're much more likely to listen to you than to me. And so you are powerful people, and I encourage you all to speak up. Thank you.
All right. Well, I'm going to come back on the screen and just say a really, really big thanks to Meg. That was really fantastic. So glad that you joined us to tell us about ocean acidification. And I think there are some fun experiments that our viewers can do at home. So thank you for showing all of those. And just to reiterate what Meg said, spread the word. Also, a big thank you to Crystal and Michael, our American Sign Language interpreters. Thank you so much for doing that. And for those of you that want to catch us next week, our NOAA Live is not happening. It's February vacation here on the East Coast, so we are taking the week off. But our sister series in Alaska that happens on Tuesdays at 3 is talking all about snow, and it's going to be a really interesting talk. So how do they predict it? How do they measure it? What are the impacts of us getting more or less snow? So I know we have quite a few Alaska folks on, and so I encourage you to just tune in for that, all about snow. And then the following week we will be back and talking about coral reefs in Texas, and you may not have even known that they have them there in Texas. It's going to be really fun to learn about that. So thanks so much to everyone. We really enjoyed the webinar today, and have a great evening or have a great early afternoon if you're on the other coast. See you later, everybody.
Bye.